All right, we want to continue on. We had a part 1 in which we introduced some of the ideas of looking at symmetry for solving some E&M problems. And what we're going to look at this time more is applying that to an interesting situation involving a submarine. In these symmetry operations, we have an x, y, z coordinate system. And one of the symmetry operations that we'll consider would be rotation about an axis. It might be the y-axis, it might be the z-axis. Here I'm showing an operation around the y. Another symmetry operation is a reflection. And for our coordinate system, the x-axis is perpendicular to the board, and the y-z plane is parallel to the board. And I've sketched in a mirror here, and the mirror is in the xz plane, so the mirror is perpendicular to the board. And when we started out in part 1, we talked about an electric field vector being a real vector, and we talked about how components would change. And the example was with your arm. If the board was the mirror and your arm is parallel to the board and it represents a vector, your arm represents a vector, in the board you'll see your arm parallel, pointing in the same direction in the mirror. So that would be the case for x and z. So for the real vector x and z, x goes to x, z goes to z. And again, if your arm is a vector, a real vector, and the board is the mirror, when you look into the board, you'll see your arm pointing into the mirror. So y goes to minus y. But the magnetic field is a pseudo vector. And all the conditions for the real vector get reversed for the pseudo vector. So we have to keep that in mind when we do a reflection. What we want to consider is the case of a point in a conducting medium in which current is flowing uniformly out in all directions, all 3D directions. I can only draw the ones in the board, but it's also coming out and going into the board. Uniform radial flow of current from a point. And we want to ask ourselves, what's the magnetic field look like? We'll assume at an arbitrary point we have a BZ component, a BY component, and a BX component. One of the symmetry operations we can do immediately is rotate 180 degrees around the BY axis. If we do that, this over here would not change, but over here it would change. And what we would get, I'll move the point over to here just to make it clear. If we do the 180 degree rotation around the BY axis, the BY will still be pointing in the same direction, but the BZ will be down, and the BX will be pointing into the board. So we've duplicated what we started out originally. We did the rotation. We have exactly the same picture. This is how the components would have rotated. So what we can say from this is that BX equals minus BX, and that BY equals BY, and that BZ equals minus BZ, and this can only be true, BX equals minus BX, if it's equal to 0, and BZ can only equal minus BZ if BZ is equal to 0. So the only component that we have left now is the Y component, BY. as a result of doing the symmetry operation of a rotation around the y direction. So at this point, we only have By. Now we'll do the reflection. I'll show the mirror displaced from the point carrying the current, and the current is a real vector, so the current will be pointing in the same directions. So we imagine that point in the mirror, and we're going to reflect the By into the mirror. But we know that when we reflect the y component, it stays the same because it's a pseudo vector, not a real vector. So over here, the y component will be pointing in the same direction. But we want to bring the picture back to the original view, which we have here, and the way we do that is we'll rotate 180 degrees around. By is this way in the mirror. When we bring it back over here, By will be pointing this way. So By equals minus By, and the only way that can be true is if By is equal to 0. So you might say, well, so what? Well, if you try to solve this using the regular integral, it gets a little complicated. It's not that hard, but it gets a little complicated. And here we showed that if you have a point with a uniformly flowing current radially outward in all directions, the magnetic field is 0. So let's get to the so what about that. So here's the point, and we have the current flowing out in all directions. And we're in a conducting medium. And we're going to consider that the conducting medium we're in is seawater. And you'll see why in a second. Now what we'll imagine is there's another point over here for which the current is flowing in. So we imagine this current going out to infinity, coming back, and now it's all flowing in here. But the magnetic field for this was 0. The magnetic field for that is also 0. So let's say that we're now going to connect these 2 points. So let's imagine we have an insulated conductor between where the current is flowing out and where it's flowing in. So we could almost imagine this being a battery like that that's insulated from the seawater. And no magnetic field from this current, no magnetic field from this current, but the total current I is flowing through this wire of length L. And that results in what is called an electric current moment. And the value of that is IL. Now, how could you actually form a current flowing like that? Well, let's imagine we're in seawater, an electrolytic solution, and we have 2 different metals. Let's say we have brass here and steel here, and maybe I have the direction of the current flowing wrong for that. But there would be a current flowing, a corrosion current flowing, and it would be as I sketched here for an infinite medium of seawater, which doesn't exist, but it's a good approximation. Now, if we look at a submarine, it has a propeller made of brass or some material like that, and the rest of it is steel. USS, I don't know what. So there is a model of this to represent what's happening here in the submarine. And so this represents a source of magnetic field from a submarine. There's also generally a magnetization, but you can also have an electric current moment contributing to the field from the submarine. And as the shaft on the submarine rotates, the resistance might change a little bit, which means that this would fluctuate. So you can have a fluctuating component to this. And there's actually a handbook which is devoted to this kind of a source. Handbook of Electromagnetic Propagation in Conducting Medium, written by Marty Kreischmann back in 1976. So what we were able to do by using symmetry operations for what looks like a complicated problem to solve of a uniformly flowing current out from a point and flowing in with a connection, we can come up with an electric current moment that represents a component for the magnetic field generated by a submarine. So there's actually a system called magnetic anomaly detection, abbreviated MAD, which has an airplane flying around with a magnetometer on it that can look for both of these components of a magnetic field.